Hey everyone, we're back and today we're going to be studying the very important topic of logistic regression. And thankfully, even though it's so important and it's very common, it's not very complicated. So this section is actually not very long, but it's going to touch on some really important ideas. So I think it'll be really a fun one and I hope you stick around to watch it. So what's going to happen, what we're going to discuss is a couple of things. So first we're going to talk about, what is logistic regression if you don't know what it is. Then we're going to talk about why you want to kind of do classification in this way. So in particular, we'll be comparing it to the generative approach that we've been talking about in the previous sections, and why, especially in high dimensions, you might want to do something like logistic regression. After that, we'll talk about forming the likelihood. So we're going to be estimating parameters using maximum likelihood. So we'll need to form the likelihood, and we'll see that just forming the likelihood in a straightforward way gives us the important cross entropy loss. And we'll show what that is, and then I'll kind of give you some more insight into where it comes from, what it means, how to interpret it. Then we'll just do our usual thing of doing maximum likelihood estimation with gradient descent. So we'll just compute the gradient, and we'll see that it actually has a really simple form. And then finally, we'll just talk about a setting where settings where logistic regression can suffer from overfitting and some easy ways of overcoming that. So kind of five points we're going to be talking about. I think all really interesting, all I think have broad applicability, perhaps even outside of logistic regression. So I think worth going through this kind of short section together. Okay, so let's start at the top. So he says, we begin our treatment of generalized linear models by considering the problem of two-class classification. That's all we're going to talk about today. In a couple of sections, we'll talk about multi-class classification. Okay, in our discussion of generative approaches, we saw that under rather general assumptions, they weren't necessarily general, so you had to assume that your different classes had had the same covariances, but sometimes that's fine. The posterior probability of class C1 can be written as a logistic sigmoid acting on a linear function of the feature vector. So that's a bit of a mouthful. So there's this, we found that you could actually write this in the case of when you had two clusters, for example, that had different means but the same covariances. There was this important, there was, in that case, we're actually dealing with just the raw feature values, and we found that the probability of one class was determined by this function, which just looks like a sigmoid. So in the feature space, when we look at things in feature space, here is one class, here is the other class, and this is, let's say, class 1, this is class 2. We found that there was a direction in space that discriminated the two. And if you went along this direction with a sigmoid, that would tell you whether you're in one class or the other. So that's the really important, this logistic function. It's just this sigmoid. Okay? And it was acting on, importantly, a linear function of the feature. So in that case, we're looking at the raw values, but you can also, as we discussed in the previous section, you can just convert, instead of the raw values, perform some fixed nonlinear transformation and work on features. Either we'll be referring to them as phi, you could put in x, whatever it is that you want. Okay, and can be written as a logistic sigmoid acting on a linear function of the feature phi, so that the probability, so the posterior probability of a class, is some function, which is going to be some sigmoid function of a linear combination of the features. And since we've only got two classes, then the probability of the other class is just 1 minus the probability of this class. So sigma is the logistic sigmoid function, which I just defined for you. And in terminology of statistics, this model is known as logistic regression, although should we emphasize this model is a classification rather than regression. Okay, so previously, and then, if you're coming in from the previous chapters, we saw that they just kind of came up. So if we modeled our data a certain way, and there's kind of some general ways that we could do that, you would always end up with a situation like this, where distinguishing the classes came down to projecting your data or your features onto one direction and applying a sigmoid. You could also just come to it, as in kind of an ad hoc way. You could say, look, why do I, care about all that stuff? I'm just going to try to see if there is some, direction in space that distinguishes my data. And I know that, I'm looking at probability, so I want a function that transforms those projections into, zeros and ones. So that could be kind of another way you could just motivate logistic regression. It's just a means of turning your, kind of, let's say, your unbounded data, unbounded, log odds, whatever it is, into a probability of one class versus the other. So that's kind of why you might, what it is. and how you might come across it. Now, why do you want to actually do this? Let's talk about kind of section 2. Why do you actually want to do this? And in particular, why might you want to do this in comparison to the generative approach? There's actually kind of a really, really good reason why. So he says, look, for an m-dimensional feature space, so m is the number of, features you have, this model has m adjustable parameters. Those are just the elements of W. By contrast, if we had fitted Gaussian class conditional densities using maximum likelihood, so if we had our data and we first tried to say, okay, what are the clusters, what are the covariances, even the common covariance? Well, we would have, for the covariance, so first for the means, we have 2m parameters for the means, because the means are different. And then we have m times m plus 1 over 2 parameters for the shared covariance matrix. So even in that setting, we have basically on something that's growing quadratically in m. And it's very common these days for m to be like in the thousands, right? So you now have to deal with, a million parameters that you have to learn. Which is going to be all the covariances. And just to make this classification, and it might turn out that all that stuff that you're using, all those parameters you're using are actually kind of irrelevant to the classification. So I'll show you this in 2 ways. So for example, let's go back to our, you guys can see this. So let's go back to our 2 classes, right? So there's class 1 and there's class 2, and we were assuming they have the same covariance. Well, in this particular case, all that matters is the projection of the data along this direction, right? So this direction tells you, because you don't care about the data itself, all you care about is making the decision. Which class are you in? And for that, all you need to know is project the data along this direction. Like all of this junk that you're modeling on the side, it's kind of irrelevant. Like you don't need to know that, okay, well, it stretches out as far as it does on that side. All you care about is a projection on this, on the direction that discriminates the 2 classes. So, and this gets this aspect of modeling irrelevancies in data, irrelevant for your decision, gets worse the more dimensions you have, right? Like you end up spending, figuring out the covariances of feature 1000 and 1050 and etc. All these useless pairs that maybe actually what matters is like they don't matter at all. You're just modeling them for no reason. Another kind of way of kind of giving you some of that is, this is kind of my favorite picture in the book. It comes from chapter 1. And let me show you. So here it is. Let me just erase some of this stuff so you guys can see. Okay, so there we go. You guys can see that? Okay, very good. So the whole point of this figure is if we look, let me get rid of these. So if we look on the left-hand side, here we're kind of modeling the 2 classes. The class conditional, we're doing the generative approach, right? We're saying what does X look like if it comes from class 2? What does it look like from class 1? Sometimes that's important. Let's say if you want to generate data, like with these the generative models these days, they're generating data. You need to model these things very well. But if you want to tell whether, let's say this could be cat and dog, you want to generate pictures of cats and dogs, well, you need to know about all of these wiggles. They correspond to, I don't know, the whiskers of a cat and like tail of a dog, whatever it is. But if you want to kind of make the distinction between them, it actually, often that distinction doesn't require nearly that much complexity, right? Because what matters there is the relative probability of these 2. So it looks like, over here in this region of space, there are these wiggles, but the probability of the second class is so low that, the wiggles don't matter. As long as, X is less than this value, you're going to be in the first class. And as long as X is greater than, some other value, you're going to be in the second class. So if what you care about is classification, you don't need to model all these wiggles. You don't need to spend millions of parameters trying to get exactly where are these bumps happening. Because what you care about is the ratios of the classes, and that can be much simpler. So just to kind of give you some intuition as to why in some settings, if you care just about making the decision, the generative approach can be a bit overkill. And it will definitely be overkill, in very high dimensions. Okay? So hopefully that made some sense. Let's make that small. So that's kind of, why you might want to take this approach. And it's not just about logistic regression. You can have, other types of, use different, instead of a sigmoid, instead of a logistic sigmoid, use something else. The main point is, for classification, you might not need all of this complexity. So it's a good idea to try a linear approach, and just try to model that classification decision, the probabilities you need directly, rather than trying to model the data first and then build the posterior from that. So key idea. I think that's one of the key ideas that I think is really important to get across. Okay, so that's why you do it. Now, how are we going to do it? Of course, we're going to do maximum likelihood in this case. So that's easy enough to do. First, a simple property of the logistic function. I'll leave this for you guys to work out. It's very simple, but so if this is, it's just a convenient property, then it goes to its derivative has this very nice expression. So if you already know the value of the function, you already know its derivative, which can be very useful when you're like building this into algorithms, right? You don't have to actually like you will have already computed sigma, so that already gives you the derivative, which is very useful. Okay, so now let's form the likelihood function. So for a data set phi of n, t of n, where the t of n's are the labels, are binary, and phi of n's are the feature vectors and they're fixed, with n equals 1 to big N, the likelihood function can be written as this, right? So we're assuming all of the samples are independent, and so it's the product of the likelihoods of the individual terms, and those individual terms have a likelihood that looks like that. Well, why is it? So, we've got what is the probability of ti xi given class 1 and given the weights. So that's kind of, that's going to be what each one of these terms. And so that's going to be, the probability of ti given, the features. I'm going to drop the 5 for now, times, the probability of xi. These are all going to be the same, so we can just ignore them. And now, so if ti, so now this is going to equal to p of c1, going to be proportional to, but, so going to be proportional to pc1 given the weights if ti is equal to 1, and 1 minus pci c1 given the weights if ti equals 0. Okay? And well, this thing here is just called yi, and this is 1 minus yi. And so we can express this expression very succinctly as, well, if t is 1, it's going to be yi to the ti, and 1 minus yi to the 1 minus ti. So you've probably seen this. We've been doing this trick since we were talking about Bernoulli things way back in the day. That's where all that comes from. Okay, so it's just picking out based on the yi's are the class the class probabilities, and given the features, and the tn's are the labels, and they're picking out which one to use. Okay, so that's the likelihood. And now we're going to, we're typically going to work with the log likelihood. Okay, so we can maximize the likelihood or minimize the negative likelihood. And if you do that, you end up with something that just looks, you can just tn times log yn plus 1 minus tn times log of that with a minus sign. We're going to be minimizing this. Okay, and this is called the cross entropy. So first of all, why is it called the cross entropy? So let's zoom in. Okay, so the cross entropy relates to probability mass functions, and so this is going to be equal to. So remember, let's just start with the entropy first, right? So the entropy was the sum over, let's say, the values that the thing could take, so 0, 1 for a single binary variable, of p of x log 1 over p of x. Okay, so that's just for 1. Now the cross entropy is kind of a similar thing, but now it's for, it relates to distributions. So it's again going to be the same thing, but p of x log 1 over q of x. Okay, so this is kind of like, there's some, maybe like some true probability, and then you could think of this as like the number of bits you're using to encode, the messages according to what you think the probability is. Okay, so now why, so why would we want to, and let's look at, actually, before we go on, let's look at how it actually relates to what we're doing here, and then we'll look at why we're, one justification. I mean, we already have a justification, right? If you want to maximize likelihood, this is what you get. So let's just think about it as kind of a little bit more insight. Okay, so what is this actually going to look like? Well, it's going to be, the sum of, we actually don't need the sum anymore. So it's going to be P of x equals 0 log of, so minus log of q of x equals 0 plus, and then it's going to be minus p of x, and the minuses are because I've taken the 1 over log of 1 over and just turned to minus log of whatever it is, times log of q of x equals to 1. Okay, well, our p of x, we're told, so these are the true probabilities for each of one of our labels. So this is actually just going to equal to, minus 1 minus tn. That's going to be so log of 1 minus y of n is going to be the probability of the class being 0 or 2, whatever it is, minus tn times log yn. Okay, so that's where, so what we have here is precisely this cross entropy. Okay, so again, that's good. So that's where the name comes from. Why is it something you want to do? Again, we saw that, okay, so if you just take the log of the likelihood, you get this. But you can also, there's actually another nice way of thinking about the cross entropy. And you can actually write it as, so this is actually going to equal to sum of px log px over q of x minus sum of px log px, right? Now, that first term is actually just the KL divergence between the true distribution and your your parameterized distribution. And the second term is just the entropy of the true distribution. Now, you don't have any control over this one. This is the one that you can control. And you're trying to minimize this quantity. So by minimizing cross entropy, what you're doing is you're actually minimizing the difference between your observed distribution, so the empirical distribution, the distribution of your data, and your parameterized distribution. So that makes sense, right? You have some parameters you can tweak. There's some observed distribution of the data. You tweak those parameters to make those distributions be the same. So by minimizing the cross entropy, we're minimizing this divergence, this difference between the true distribution and your parameterized distribution. Okay, so that kind of gives you some insight into what's going on here. And there's this notion of maximum likelihood, maximum likelihood being reducing the KL divergence between the true, the empirical distribution and your parameterized distribution. That's a general property of maximum likelihood, which you might get into in another video, but it's just a very simple analogous derivation to this. Okay, so that's where cross entropy comes from, and a couple of motivations as to why you might want to use it. But here, it just fell immediately out of the note, of forming the likelihood and then wanting to maximize it. Great. So that's it. So that's the likelihood and the cross entropy bit. So now, how are we going to do maximum likelihood estimation? Well, the simplest idea is to just do gradient descent on this thing. Now, quite remarkably, it turns out that the gradient descent on this object, on this energy, actually gives you exactly the same updates as you would, in the linear regression case, as if, when you were treating y of n and t of n as, you imagine, and there was no link function, so there was no sigmoid. We just had these fixed features, and we're just treating the data as, some just happens to be binary. Linear regression can, deal with real value data. Just happened to be binary, and we were trying to fit it with by just finding some weights, and there was no sigmoid. It was just the linear weighting of our features. So that's quite cool. It's and so this is just easy enough to do. We can just do it for one of the. Let's just do it for one of the samples. So if we take let's zoom in again. Right. So if you just go dw, so it's going to be what? So it's going to be tn over yn times yn. I'll use the dash for the derivative. There's probably a minus sign going to be hanging out there. Plus 1 minus tn over 1 minus yn, and there's going to be a minus sign times the yn, right? Just because of this. Okay, and then that's going to be hanging out there. Then we're also going to get, so on the outside is going to be the derivative of the sigma function. So there's going to be the derivative of sigma, and then it's going to be, then we're going to be just left with the linear term, which has got w transpose phi. So the derivative of that with respect to w is just going to be the phi of n. Okay, so all we do is now we just kind of multiply this across. So the main the main interesting thing that happens is we're going to get this yn times 1 minus yn term on the bottom, and on the top from this derivative term we're also going to get yn times 1 minus yn. So what that's going to do is it's just going to cancel. So these two things are just going to cancel each other out. So all we're going to be left with is phi of n. When you multiply everything across and subtract, you'll get this difference term showing up, and that's where you get this full expression. And I think it's quite remarkable. I don't know if it's, if it happens, by accident or not. Like, is it just an interesting coincidence? He doesn't really comment on it. He just says, well, precisely the same form as a gradient of the sum of squares error function. I mean, so that's great news. Like, is there a reason why that happens? So I couldn't come up with a reason myself. Just a couple of things to just point out. So most of this, so all of this doesn't really depend on the form of the sigmoid, right? So if we start with, the yn is already after the sigmoid that we've applied. So everything that just involves yns is going to be there no matter what function you use. So ultimately, what you're going to end up getting is, if we let me just erase all of this. Ultimately, what you're going to end up getting is something that looks like this. Erase all of that. So if we actually didn't cancel things out, we just left them in, you would get a y of n times 1 minus y of n. That's just going to be there anyway, times the derivative of sigma times phi of n. And so it just so happens with the logistic that these two cancel out. Oh, and we've already included the phi of n. So this is going to be there. This is the most general form of that coefficient hanging out. So it turns out for the logistic, it cancels out, becomes 1. But actually, in general, it's always going to be, for reasonable functions, for reasonable functions mapping the projections onto probabilities. This part's going to be positive. This part, unless we'll see in a case where this will be problematic, but let's assume on realistic data sets, this will be non-zero and positive, because the yns will be between 0 and 1. So effectively, your gradient is always going to be proportional to whatever it would be under the regression case, up to some positive scaling factor. And so when you set this thing to 0, when you try to solve it that way, rather than going down a gradient, if you just want to, let's say, use root finding techniques to find a solution, you will get, it seems to me, you would get the same solution as if you treated it like that original regression problem. So I haven't kind of thought any more about why that should be the case, but just kind of just an interesting observation I wanted to kind of flag out for you guys. But anyway, for the logistic regression case, it turns out that it is actually exactly, you don't have to, remove positive scaling factors. It turns out it's exactly the same as if we didn't have a link function and we were just doing linear regression. Okay, and now when you've got this gradient in hand, then you could do your own updates. And if we desired, we could make the use of result 4.91 to give a sequential algorithm in which patterns are presented one at a time and the weight vectors are updated. Okay, so you could just do your own stochastic gradient descent. We'll see in the next section that because logistic regression is actually quite a well-behaved loss function, so it's actually more efficient to use the curvature information to make convergence faster. So we'll see that in the next video. Okay, and finally, let's just talk about topic 5. So when do things overfit? I'll give you a simple example of it. So before we just read that, let's just zoom in. Suppose here is we're going to put a positive. So this is our positive example, and this is our negative 1, whatever. Or this is the one that we want to be. This one should be labeled 0. This one should be labeled 1. And just for the sake of simplicity, we'll have them be evenly distributed. So essentially, what's going to happen is, okay, let's just start with some guess at what let's say we start with some guess like that. Actually, to make it more, let's just look at a really fat. So maybe this probability is like 0.9. This is 0.1, whatever. Okay. So now if we make this thing steeper, well, it'll kind of go like this. And the probabilities will increase, and they'll actually match our data better, right? Because we said the probability of this should be 1, and now this will get closer to 1. So maybe it'll become 0.99, and this will become 0.01. Well, let's keep making it steeper, right? And how are we making it steeper? Well, we know that this thing is, the sigmoid is 1 over 1 plus, oh, let me just a little bit over so you guys can see. No, we've got, this is going to be sig of w is going to equal to 1 over 1 plus x minus w times our data points, which is sitting at -1 and +1. So the way we're doing it is we're just increasing w. So as we increase w, it becomes sharper and sharper, and the probabilities get better and better, right? So as far as maximum likelihood is concerned, this is great. We're matching the data better and better and better, and it won't stop. So w will get arbitrarily large. Things will blow up, and it's very unlikely that on a new data set you will get the right answer because you've kind of overfit to this one. So the natural solution is just to add a regularization term, equivalently put a prior probability on w. So you can say, well, let's say p of w is, if you don't have any data, is coming from some normal distribution with some variance, and so that will just push. If w gets too large, it will keep it, it'll keep it from getting too steep. And so instead of doing maximum likelihood, you can do maximum a posteriori, that includes the contribution from this prior. Equivalently, you can just add a regularization term. So that's kind of what we're talking about here, so you guys can see. That maximum likelihood can exhibit severe overfitting for data sets that are linearly separable. And you might think this doesn't come up that much, but again, we're dealing with, so in the old days it didn't, when you didn't have that many parameters, and you had lots of examples, then it was kind of unlikely that your 1,000 points of your dimensions are going to be linearly separable. But now we have kind of the reverse situation where you have like 100 points in 10,000 dimensional space. Frequently, they are linearly separable. So what you want to do is you need to actually worry about this now. So this overfitting arises because the maximum likelihood solution occurs when the hyperplane corresponding to sigma equals 0.5, so like this one, equivalent to wt phi equals 0, separates the two classes, and the magnitude of w goes to infinity, as we saw, right? Because you can just fit the data as far as maximum likelihood is concerned better and better. In this case, the logistic sigmoid function becomes infinitely steep in feature space, corresponding to a heaviside step function. So that's what we saw. So that every training point from each class is assigned a posterior probability of 1. Right? So this data point was given it's coming from the 0 class, and its probability of 0 class is going to be 1. What we're showing here is the probability of its 1 class. Furthermore, there's typically a continuum of such solutions because any separating hyperplane will give rise to the same posterior probabilities at the training data points. So I think what he just means is like you can also, that'll also be a solution, etc. Maximum likelihood provides no way to favor one such solution over another, and which solution is found in practice will depend on the choice of optimization algorithm, okay, which is not necessarily what you want. Note that the problem will arise even if the number of data points is large compared with the number of parameters in the model, so long as the training data is linearly separable. So indeed, right? So the main thing is just linear separability, but as I mentioned, that gets more likely when you have few samples compared to the feature numbers. And the singularity can be avoided by the inclusion of a prior and finding a map solution for W. So that's what we said here, or equivalently by adding a regularization term. So you take the log of PW and you add that to that likelihood function we had, and it's going to end up with something like a W squared over 2 sigma squared or something showing up. So now that's going to prevent you from making W very, very small. Okay, I think that's all I want to talk about. So I think logistic regression is very useful. It comes up all the time. But I hope you got the idea that it's not very complicated. Basic idea is actually quite simple. Something you might come up yourself. You have data that you want to separate, so you kind of look at it from, okay, let's say there's a linear direction in data that separates my classes, and now I need to map the probabilities, so I could use a sigmoid to do that, and then the rest is just maximum likelihood machinery. You can also think about it coming from the generative view, where we saw that this just emerges naturally. If you, for example, assume there are 2 Gaussian clusters with the same covariance, you get the probability of one of the classes having this property, having this shape. And we saw, I think really importantly, that when especially in high dimensional spaces, if you care about classification, you might want to just work with these kind of classification, these decision functions directly, rather than going through the generative approach of modeling the different clusters and then computing the class probabilities, because that's just going to the number of parameters kind of blows up. And then we did, the maximum light, and then we talked about cross entropy. Sorry, I forgot about that, which is, again, comes up all the time. You'll see it in neural net training all the time. And we kind of motivated that as well. It is the log likelihood of the data, but it's also, you can see, as minimizing the KL divergence, the difference, type of difference between the true your data, so your labels, and what your model is predicting. Cool. So I think that's essentially all I wanted to talk about today. And next time we're going to use the special properties. Well, we're going to use the fact that the loss function for the logistic regression is quite well behaved. So it will actually respond quite well to using curvature information rather than just going down the slope. And we'll talk about something called iteratively reweighted least squares for doing that. So I hope you learned some stuff today. Hope you had some fun. Please let me know, as always, if you liked it or if you didn't like it. And I will see you in the next video. Bye.